Yeah, so today I'm talking about like random matrix theory and eigenvalues. So the collaborators on this work, it's Ben McKenna, he's at Georgia Tech, and also my advisor, Mark Selke at Harvard, or one of my advisors. Yeah, so I'll try to convince you guys in this talk that this sort of random matrix and large deviation stuff, it's also interesting to people in computer science or physics or sort of applied math, not just in like pure math necessarily. Okay, cool. So let me first give a primer on random matrix theory. So the main question in random matrix theory is basically, suppose you have a matrix with random entries. What can you say about the probability distribution of the eigenvalues? So to illustrate this, let me first go over one of the most canonical examples, if like the most canonical example. This ensemble is called the GOE ensemble. Basically, consider this method of generating a random matrix. So let's say you have a square matrix, and suppose the matrix is symmetric, so the eigenvalues are real because the matrix is symmetric. And suppose basically the matrix is just pure Gaussian noise. So the off-diagonal entries are centered with variance 1 over n, and the on-diagonal entries, let's say, have variance 2 over n. OK, and just as a fun fact, this ensemble is actually rotationally invariant. So basically, if you take an orthogonal matrix, like an arbitrary rotation, then x has the same distribution as like basically just change basis to some like whatever rotation. OK, so the important question that we care about is like, what does the distribution of the eigenvalues look like? So to do that, I asked ChatGPT to plot it using Python. Basically, it looks something like this. It turns out that for large n, the eigenvalue distribution will converge to this semicircle. So here's like the histogram of the eigenvalues. This orange dotted line is the theoretical distribution, like what it actually converges to when n goes to infinity. This is called the famous Wigner semicircle law. So formally, what's going on is let this be the empirical measure induced by the eigenvalue. So it's like the sum of all these like point masses, basically. And let's define this to be the semicircle measure. And the semicircle measure has this density. So that's literally a semicircle because it's like y equals square root of 4 minus x squared. Then basically, almost surely, and let's say Waterstein distance, or whatever distance of probability metrics, really, you have that the semicircle law, you have that the empirical measure will converge to the semicircle law. So this is one of the most like celebrated results in random matrix theory. It's kind of like the central limit theorem of like random matrix theory. So I guess if you're studying, let's say, statistics, before you can do hypothesis testing or have confidence intervals or whatever, you first need to know that the central limit theorem holds, right? So you know like what the limiting objects are. In random matrix theory, the first step is kind of just to understand what do these limiting objects look like. OK, so maybe there are also some nice examples here of other limiting distributions. So imagine you take a GOE matrix, which is kind of like that pure noise matrix. And let's say you shift the diagonal entries by a bit. So you divide the matrix into 2 by 2 blocks, let's say of equal size. For the top left block, you add, let's say, -5 to all the diagonal entries. To the bottom 5, you add 5 to all the diagonal entries. And this kind of takes the semicircle and kind of like shifts it in some directions. OK, and maybe another example is, what if you apply what we call a variance profile to the Gaussian, to the GOE? So imagine you're doing the same thing. You take the GOE matrix and you split it into 2 by 2 blocks. Now, instead of all the entries having variance like order 1 over n, let's say the top left entries has variance like 0.1 over n. The off-diagonal ones have 5 over n, and the bottom right has 10 over n. The off-diagonal ones have the same variance because the matrix is still symmetric, so the eigenvalues are real. Anyway, then you get this sort of like nifty distribution here. That's like kind of nice. So I won't talk about this too much today, but there's a lot of like theory on how do you compute, what are these limiting distributions look like. You can actually compute, let's say, the formula for these curves and like what these limiting objects actually behave like. So I'm happy to talk about that later, but some buzzwords to throw out are like free probability and vector Dyson equations. Though a lot of those tools you can use to compute these limiting objects. OK, so another interesting thing in random matrices is maybe this BBP phase transition. So what is this? So imagine we have, let's say, a GOE matrix, which is basically all noise, plus some signal. So you imagine like, OK, this is some signal in the data. You're like adding some rank 1 perturbation. And lambda is, let's say, the signal-to-noise ratio. One comment is that the GOE matrix, as I said, is rotationally invariant. So the choice that I made to use E1, the first standard basis vector, is sort of arbitrary. It can be any unit vector, and this result will still be the same just because you can rotate everything. But basically, the theorem says that when n goes to infinity, the top eigenvalue will converge to 2 if lambda is less than 1, and this if lambda is greater than 1. So what does that mean? So basically, note that for the semicircle law, the equation is square root of 4 minus x squared. So that the rightmost edge is exactly at 2. So this is basically saying that when the signal here, lambda, is sufficiently weak or is like not sufficiently strong, there's not going to be any sort of outlying signal that occurs. So for example, let's say like you have a data matrix and you're doing PCA. What people like to do is like, oh, you take the PCA and then you take the top eigenvalue, right? And you say like, oh, the top eigenvalue, the top eigenspace corresponds to some signal. So basically what this is saying is that if lambda is not big enough, there's no signal, like no outlier eigenvalue that's going to pop out. But if the signal is strong enough, you're going to have an outlier eigenvalue there. And to prove that I'm not making this up, I also use generated using Python. So what happens is basically most of the bulk distribution, so the bulk spectral distribution, converges to the semicircle. But if you look closely, there's some like outlier eigenvalue that actually showed up. Yeah.
Sorry, I missed something basic about this. Is this the distribution of all of the eigenvalues or the distribution of the maximum eigenvalue? Or?
Oh, sorry, yes. This is the histogram of all the eigenvalues. Yeah, so basically most of the eigenvalues are still going to be like from the pure noise. But then you have this sort of rank 1 signal. And then you have like one, like let's say, signal eigenvalue that jumps outside. And yeah, basically, heuristically, you might imagine that the eigenvector corresponding to that signal is like roughly speaking E1, or it's like pretty parallel to E1. Yeah. Yeah, thanks for the question. Yeah, so this is another theorem that we have. Yeah, OK. One more thing is that you can also do this for the singular values of random matrices. So this might be more interesting if you actually care about data. But basically, imagine you have like a rectangular data matrix. And let's say, again, like the matrix is pure noise. The limiting object here is also well known. You can derive it. And the shape sort of depends on the aspect ratio, like this ratio m over n. Yeah, so like yeah, if you're doing PCA and like you have an actual data, you could just do this, like plot all the singular values. What will happen is you'll probably get some like bulk distribution of the singular values. And then you might have some signal eigenvalues that lie outside if you actually have some signal, something like that. So the next slide. Yeah, OK. So I guess here I've talked mostly about limiting distributions. Like what's the limiting behavior of these random matrix ensembles? And again, that's like the first step in random matrix theory. Just like in statistics, you need to first establish the central limit theorem. Here in random matrices, we need to first know what these limiting objects look like before we can say anything else. So what are we interested in? We're interested in what I'm going to call large deviations or atypical eigenvalues. So I actually drew this, so in case you thought it was impressive. But basically, imagine like you generate x from the GOE ensemble, so you have some like this pure noise matrix. It's possible that the eigenvalue distribution looks something like this. So for example, like most of the eigenvalues like lie in this semicircle bulk, but maybe just due to random chance, just due to the variance, there's some eigenvalue that jumps outside of the bulk and lands in some like interval near u. And and what our goal is basically to characterize what is the probability that this kind of rare event happens. This is what we're going to call like a large deviation. It's kind of sort of a large deviation from the standard behavior. It turns out the probability of this event is captured by what we call a large deviation principle. You can show, or we will show, that the probability that there exists an eigenvalue in this interval, it's going to go to 0. It has to go to 0 because you know that the limiting object is the semicircle. But it goes to 0 at exponential speed. And the speed here is n, and the I of u is some rate function that depends on u. So that's the probability you have an eigenvalue near u. I want to say that we're not the first people to do large deviations, but we are introducing sort of a new technique here. I'll talk about that briefly in a brief literature review. But now I'm going to, yeah.
What is the speed?
Oh, yeah, so the speed, so n here is the dimension of the matrix. So basically, the speed is like how fast, like the exponential rate at which it goes to 0, and it's like dependent on the size of the matrix, basically. Yeah, but this I of u shows like that's like called the rate function, where n is like the speed. It's like e to the negative n, but there's a constant, and the constant is like that rate function basically. Yeah. OK, so now I'm going to try to convince people that maybe you could care. Yeah.
Sorry, constant that depends on u or constant?
Oh yeah, it's some function I of u.
Okay.
Yeah. OK, yeah, I'm going to try to convince people that maybe even CS people, physics people can care about these sort of problems. I think one of the most intuitive ways to understand why you might care about these results is sort of in asymptotic statistics or asymptotic hypothesis testing. So suppose oh, I also drew this by the way. Yeah. Suppose I gave you the following distribution and you want to do some sort of statistical test. So I'm like, OK, I give you these eigenvalues. Most of them are in the semicircle, and you have this outlier eigenvalue. So there are two cases. Your null hypothesis might be OK, well, your random matrix ensemble has no signal. It's just pure noise, and it's just due to chance or whatever, you have this outlier eigenvalue that jumped outside. Or your alternative hypothesis is OK, well, there's actually a signal. Maybe you have some rank 1 signal, and this distribution is actually from this the ensemble with the signal. Now, if you want to reject the null hypothesis, you need to sort of quantify what is the probability that you have an eigenvalue that jumps outside. Or if you care about data, like what's the probability that you have a singular sort of value that sort of jumps outside of the bulk, right? Because if you can't say like how unlikely this event is, then you can't really like reject the null hypothesis or whatever. Yeah, so some applications, like if you're doing some asymptotic statistics or like some sort of asymptotic studies of PCA, this might be relevant. So maybe another example in graph theory. So I'm not too versed in graph theory, but I understand that I think people care about these sort of things. So let's say you're doing some hypothesis testing to test between Erdos-Renyi and planted-click random graphs. So what are these? So Erdos-Renyi random graph is basically a graph on n vertices, and you generate each edge with probability p independently at random. So it's like a pure noise graph. I don't know, you can think about it that way. What a planted click is what you first do. Let's say you have n vertices. You can take k vertices and draw all of the edges between them. So you have like a complete subgraph there, and you plant that click in the graph, and then you generate all the other edges sort of randomly with probability p. So you sort of have some like underlying signal there. So you might care about like if you study these kind of problems, like okay, how strong or how big does this click need to be in order for you to like think like, oh, there's a click. This is not just random noise. So you might think like your null hypothesis, if I actually give you a graph and it has a click of size k, you might think the null hypothesis is like, oh, OK, this graph is just from an Erdos-Renyi graph. And just by chance, you had this like big connected component, whatever, or click, not connected component. Or you might be like, OK, this is way too unlikely. The graph has got to be a planted click. There's no way this actually happened. And again, this is sort of like talking about what is the probability of large deviations in these rare events. So this doesn't necessarily have to do with random matrices, but it does have to do with these sort of like rare events questions. OK, so now I think so pivoting a little bit, another interesting question is that you care about in random matrices is not just the probability of an outlier eigenvalue, but what is the properties of these like eigenvectors that actually created them. And people in physics and I think statistics and people in CS could also care about these. Anyways, so OK. So what can large deviations tell us about eigenvectors? So suppose that we generate this GOE matrix, like that semicircle matrix, and the largest eigenvalue happened to be 3. So you might wonder, like, OK, so how can one generate such a large eigenvalue? How could that happen? Maybe one possibility is that, OK, well, just by chance, maybe one entry of x, let's say the top left entry, the 1/1 entry, just happens to be like really, really big somehow. Maybe it's like the top left entry is literally equal to 3. And then the corresponding eigenvector would probably be the first basis vector. You just put all of your mass on like that top left entry, right? You kind of go all in on that top left entry. And by the way, x11 being large, being 3 actually is very large because its variance is on the order of 1/n. So this is basically one way you might imagine that you have this outlier eigenvalue that sort of happens. Maybe another way is just like, OK, so maybe many entries of x just happen to be like a little bit bigger than usual. And then the corresponding eigenvector sort of has more evenly distributed mass across its entries to sort of accumulate all of those like small, larger, smaller than average, whatever, something like that. OK, so then the question is like, OK, well, if you actually do see a big eigenvalue, which case is it? Like, what should the corresponding eigenvector look like? So consider something like this. So say you do some math, and you say that you conclude that the probability of case 1 is roughly on the order of like e to the negative c1 times n for some constant c1. And the probability of case 2 is like e to negative c2 times c1. And suppose you computed that c1 is bigger than c2. Well, then the point is that when n goes to infinity, this probability is like exponentially larger than this probability. So that kind of means like, OK, if you do see a large eigenvalue, it's basically always going to be case 2 that generated it, because like it's like exponentially more likely than the first case. So yeah.
There's something that confuses me about this. Like,
yeah.
Maybe just like philosophically, since everything is like rotationally symmetric, and I could have just been like thinking of like working on the basis of whatever this evenly distributed eigenvector is.
Oh, right, yeah.
It's not like morally really the same case or something.
Oh, yes. OK, so sorry, this is kind of a bad example because, yeah, you're right. It turns out there's a theorem that says for the GOE ensemble, all the eigenvectors are like rotationally invariant indeed. So this is kind of like not true. Like you won't really have this like 1, 0, 0 thing. So maybe this is actually a bad example because you're very smart and notice that. But the point is like in general, like the idea is like you might have some cases that are not rotationally invariant. And the point is like if like one configuration is way more likely than the other, if you do see an abnormal event, it's always going to be the most likely configuration that caused it. But you're right. This specific example is kind of bad because the eigenvectors are rotationally invariant. Yeah. Does that answer your question?
Yeah.
OK, yeah. So this is kind of a poor example. But the point is that this also gives you eigenvector information just because it's like, at exponential scale, if you have an unlikely event, the event that caused it is going to be like the optimizer of the probability. It's going to be like the most optimal configuration that sort of causes that. So as an example, like, OK. So let me first explain what I mean by localization and delocalization. An eigenvector is localized if like a constant fraction of the mass is on one coordinate. So this vector is localized because basically all the mass is on one coordinate. But if all of the entries of x are like equally distributed, so if you take a vector uniformly distributed on the sphere, all of the entries will be on the order 1 over square root n, like with high probability. That's we call it delocalized, because you don't have like a lot of the mass on that coordinate. So, so consider the following example. Like suppose you have some random matrix ensemble with some parameter j of interest. Let's say maybe j is the signal to noise ratio. Maybe what happens is that when j is bigger than some j star, the optimal configuration, or like the configuration that maximizes the probability of a rare event, happens to be for localized eigenvectors. And maybe when j is like less than j star, it's like delocalized or something. So this would be some sort of phase transition that happens exactly at j star. Not only can you say like, OK, this is the probability of a rare event, but you're also saying like, if a rare event happens, this is like what caused it, basically. And this is quite relevant in mathematical physics. I believe in quantum computing as well. I think they care a lot about localization and delocalizations of like quantum states. Allegedly so. Yeah, something like that. OK, so the last motivation I want to give is kind of like talking about optimization algorithms a little bit. So consider a tensor PCA setting. So what is this setting? Imagine you're given data from this model. So y equals, let's say, a rank 1 signal. So this is like a unit vector tensored k. This is some signal to noise ratio plus some like symmetric noise tensor or whatever. So the name of the game in this problem is you want to, if I give you this tensor, I want you to be able to tell me what is the direction of the signal. So you want to recover u, because that's the signal and w is the noise. You could consider doing some like maximum likelihood estimator. It turns out the maximum likelihood estimator in this case is just to choose sigma so that this dot product is maximized, where sigma is on the unit hypersphere. And you might want to like, you could compute this maximizer using some like Langevin dynamics or some like gradient flow, gradient descent or something like that. And if you want to study like, OK, well, how do these optimization algorithms perform, you need to know something about the landscape. For example, like how many critical points there are, how many local minima, whatever. It turns out that in this paper, they show that the loss landscape actually depends on certain large deviation rates, like those kind of probability, those things that appeared in the probability. So at least in this work, it shows that like even if you don't care about like what's the probability of these rare events, because they will never happen in real life, it turns out that they can also be relevant in actually studying like the performance of algorithms, because they sort of play a role in like what the loss landscape actually looks like. Yeah, so I think that's the maybe a brief literature review. OK, since I think there's slightly less time than I expected, we can skip this. But the point of the literature review is there are other ways of computing these large deviation principles other than what I'm about to propose. But they sort of have a few limitations that are that we can sort of get around. OK, yeah. Feel free to interrupt me anytime, by the way, if there are questions. But this will conclude the motivations part of the talk. OK, so let me first tell you about what random matrix model we're looking at. So in the back of my mind, you can always consider kind of the GOE matrix. But basically, imagine you take a square matrix, kind of like the GOE matrix, and split it into a few blocks. So let's say you partition the coordinates into two what we're going to call species. Let's say like you partition the first third of the indices into one species, and the other like 2/3 of the indices into a second species. You just partition the coordinates into like 2 blocks. You can have more than 2 blocks. I drew this myself, so it's hard to draw more than 2 blocks. Anyways, but yeah. OK, so then what do? You split into blocks. Now you allow each block to have an arbitrary variance. So here, like instead of all the variances being on the order of 1 over n, here you scale the variance to be on the order of like gamma 1, 1 over n. So you kind of have this matrix with all these variances. And then what you do is I allow you to take all the diagonal blocks and add like a diagonal shift. And this sort of will shift the masses of those humps of eigenvalues, as you saw sort of previously. So these models, so why do we study these models? They're basically harder than the GOE, but easy enough to solve. They're also relevant in certain like physics settings. Like you might imagine like a lot of these like random matrix things sort of also come from spin glass theory, like these sort of these like high dimensional random functions, and like allowing like different variances is sort of a pretty natural extension. But yeah, so this is the model where you should have in mind during the talk. Our results also work for rectangular matrices, like the singular values of rectangular matrices. But for the talk, I'm just going to focus on the square case. The rectangular case is pretty analogous, actually. OK, so this is the random matrix thing we're looking at. OK, so formally, yeah, you fix the number of species S. You partition the blocks into those fractions. You can scale the variances, and then you sort of add some diagonal perturbations. Right. One thing I want to just mention before I move on is this ensemble actually satisfies a rotational invariance property. So remember that the GOE is rotationally invariant to like rotations. So basically, this one you might imagine that because we're sort of splitting it into blocks, if you just like rotate this block and rotate this block separately, then the whole thing will still be rotationally invariant. Because each of these, this is basically just a GOE matrix with a variance scaled. So if you just rotate this arbitrarily, just because the GOE is rotationally invariant, this should also be rotationally invariant. So what this is basically saying is if you take an orthogonal matrix, so that like it's basically a block diagonal of smaller orthogonal matrices, what happens is our matrix X that we generate will be orthogonally invariant like within species. It will satisfy something like that. Again, it's just because the GOE is rotationally invariant, so if you rotate within the species, everything should be fine. Yeah. OK, cool. OK, what is one consequence of this? So this will be related to eigenvectors. But consider the following math, I guess. So if you consider something like this quadratic form, so sigma is like a unit vector. So this quadratic form, this has the same distribution as this, just because x and O transpose XO have the same distribution. And let's define sigma prime to be equal to O times sigma. So what's the relationship between sigma and sigma prime? Well, basically, the point is like if you sort of partition the coordinates of sigma into like these different blocks, the same as you partition the indices, same with sigma prime. The point is that the L2 norm of sigma I will have the same L2 norm as sigma I prime, since they're just rotations of each other, right? So they'll have the same L2 norm because like they have the same like mass, so to speak, but you're just like rotating them around, so they have the same L2 norm. OK, so what is the point of this? It turns out that when we do the math later, you're going to have a bunch of functions in terms of like these vectors sigma, and it's going to be convenient to rotate these sigma so that basically you put all of the L2 norm of each like one of these subvectors onto the last coordinate of like those independent species. Yeah.
I have a technical question from the last.
Oh yeah, sure. Yeah.
So is the sigma i's are coordinate? Like why is it that the coordinates have the same L2 norm if I rotate?
Oh, sorry. It's like the subvector of those coordinates.
Subvector corresponding to one of the blocks.
One of the blocks, yeah, exactly. Yeah. Yeah, that's a good question. Yeah, thanks. Sorry if that wasn't clear. But yeah, you basically have these subblocks, and because you're rotating each of the subblocks, that's why they have the same L2 norm. Exactly. So the point is that when we do the math later, you can always just sort of, turns out you can rotate these vectors so that all of their mass lies on, like, let's say, the last coordinate of each one of the partitions. And what is the point of this? The point is that it turns out our results will only depend on what is the distribution of mass among each of the different blocks. Like how much weight do you assign to each different block? And the number of blocks is independent of n. So now you have some like low order statistics that you can track. So previously I was talking about like, what's the optimal configuration of eigenvectors? Like if you have a rare event, what is the corresponding eigenvector going to look like? It turns out that the optimal eigenvector, for an eigenvector to be optimal, the optimality condition is basically just in terms of how you distribute the weight among the different blocks. And basically that's going to like tell you the information about what these optimal eigenvectors look like. Yeah.
You're saying low order, I should imagine like 2 blocks and like 2 subvectors or something.
Yeah, or 5.
Or 5.
I mean, 50 is also OK. Yeah, as long as it's not increasing with n. I think our results do allow you to increase with n, like maybe if you increase like square root n log of n. But anyways, at least this doesn't cover that. But yeah, I just mean independent of n. OK, awesome. OK, so let me give you an informal sort of summary of what our main result actually says. It basically says, OK, so if you have a vector that's split between blocks, like these subvectors, let's define its weight profile to basically to be the vector of like L2 norms here. And note that these numbers sum to 1, because this is a unit vector. So all these L2 norms should sum to 1. I mean, they do sum to 1. So basically, the main result is to compute this rate function that kind of says like this. So the probability of xn of the random matrix having an eigenvalue near u, so this is like outside of the bulk spectral distribution, near u whose corresponding eigenvector has this weight profile is on the order of e to the negative n times this function. That's basically what's going to happen. Then if you want to know what's the probability that xn actually has an eigenvalue near u, Well, again, the optimal configuration here is like, what's sort of the optimal configuration that maximizes this probability? Well, then it should just take like the infimum over like the constraint that this is a unit vector of this function. So this kind of says like, OK, well, not only does this tell you what's the probability of having an eigenvalue near you, but the point is like, if you have an eigenvalue near you, the corresponding eigenvector, what does it look like? Basically, its weight profile should exactly be the one that like optimizes this like weight function. That's kind of the main. That's kind of in a nutshell like what we're trying to prove. OK, awesome. Oh yeah. OK. So So then yeah.
Just to make sure I'm following.
Yeah, please.
So far, you haven't said like the interesting thing, which is like what I is as a function of the weight profile, right? Or
Sorry. Yeah.
you haven't said like the interesting thing, which is like what I is as a function of the weight profile.
Oh yes, I'm going to derive that now.
Okay.
Yes.
So far, you're just like it only depends exponentially on the weight profile.
Oh yes. Roughly speaking, this is what's going to happen, and now I'm going to like try to compute I. Yeah. OK, so this next few slides are actually kind of fun if you like math, I guess. I don't know. but basically, there's this thing called the Katz-Rice formula. So the Katz-Rice formula, in a nutshell, if you have like a random function, it allows you to compute the expected number of zeros of a random function. So here, let's say you have a function f defined on some manifold m that outputs real numbers. And you don't really need to know what a manifold is. It's not too important. But the reason it could be random is like its domain is like the manifold. But it might depend on some like latent Gaussian random variables or something. That's like where the randomness might come from. This basically says the expected number of zeros of f is, OK, you integrate along the domain. Here's the manifold of the expected norm of the derivative conditioned on f being a 0 times the density that f equals 0. So this looks kind of mysterious. So let me give a pretty heuristic derivation. So let's say you have a function f from 0 to L to R. So this function, to be clear, it's like f of x. But f of x could also depend on some like g1, g2, gn, where those are like some like coin flips or some like Gaussian random variables. OK, so what does this say? So the expected number of zeros of f, sort of by definition, it's like the sum of the delta masses where like f of x equals 0. This is sort of by definition, if you don't care about measure theory, that is, which is all good. But anyways, but you have this by definition. Now let's do a use substitution, y equals f of x. OK, so then the domain, instead of being the image, it goes back to 0 to L. So instead of delta of y, you have delta f of x. And then when you do dy, it's like dx times like f prime of x, just by like chain rule or something. I don't know. Anyways, OK. So now if you move the expectation into the integral, which you can do because you don't care about measure theory, basically you get this inside the integral. And how do you get this like conditional thing? If you want to move an indicator to the condition, you just need to multiply by the density on the outside. So like this density times this gives you like this joint sort of conditional term. Yeah, so it is more or less kind of more or less intuitive. You can kind of think about this as like, OK, if you condition on the event that you have a 0 near x, and if the derivative is really big, that means it fluctuates a lot near x. And if it fluctuates a lot near x, you might like expect to have more zeros around there or something. OK, but maybe to give a better example, here's like the sort of party trick that I quite like, actually. Oh, wait, hold on. That comes next. OK, yeah, let me first discuss this. OK, so this formula allows you to count the expected number of zeros of a function. You can also count the expected number of critical points of a function. And by the way, there are some papers that sort of talk about loss landscapes of neural networks or like these high-dimensional random functions. And they say like the expected number of critical points or the expected number of local minima or whatever. That's just using the Katz-Rice formula, because you can use the Katz-Rice formula to count the expected number of like critical points of these high-dimensional surfaces. OK, so what is a critical point? A critical point is when the gradient equals 0. So if you want to count the expected number of critical points, that's basically just the expected number of zeros of the gradient. Right, so what you can do here is something like this. So let me first go over the Katz-Rice part. So if you're counting the expected number of critical points, that's the expected number of zeros of the gradient. And by the Katz-Rice formula, that's like the norm of the gradient, which is the Hessian, conditioned on the event that the gradient equals 0, and then times the density that the gradient equals 0. Say you want to know the number of critical points so that like the function itself is in some interval, then you can basically just add an indicator and like integrate over like those points in the indicator. So yeah, this is actually, there are a bunch of papers on like, they study like spin glasses on hyperspheres, and they say like the expected number of critical points, is whatever, and therefore the landscape of whatever is something. Basically, they're just using this Katz-Rice formula. Then people might conclude like, that applies to neural networks, because neural networks are also kind of like these high-dimensional random functions. Whether or not you believe that is sort of up to you. but there are some papers using these high-dimensional Gaussian random fields, and yeah, they may or may not apply to loss landscapes. Who knows? But this is like the main tool they use. Okay, so here's the party trick. So this is kind of fun. So suppose you have f of x. It's this infinite series. So the sum of g0 plus g1, and each of these coefficients is a standard Gaussian random variable. Can you compute the number of zeros of f of x? There's the expected number of zeros for x in that interval. OK, so what you do is the following. So f of x just equals this. If you just differentiate it point-wise, term-wise, you get kind of like that. And the point here is that f of x and f prime of x are jointly Gaussian random variables because they depend on the same Gaussian random variables. So you can write down their joint distribution. And the point is then you can use the Katz-Rice formula. So the Katz-Rice formula does involve this sort of scary conditional thing. But the point is that for jointly Gaussian things, conditional distributions are actually very easy to compute. So long story short, the answer is this. So this is kind of a fun result, I think. It's kind of neat. But it turns out that that's true. So this is one kind of fun example of the Katz-Rice thing. OK, so now the question is, OK, so what does Katz-Rice have to do with random matrices? So let me do a little bit of setup. So let me define the unit hypersphere to be that thing. So this is the n-dimensional hypersphere. Oh, yeah, please.
Sorry, can you do the theorem of the previous slide slower? This is the expected number of zeros.
Oh, yes, sorry.
Function is the arctan of the interval that you're interested in.
Oh, yes. So f of x is like this infinite power series, and the coefficients are independent standard Gaussian random variables. Yeah, so the Katz-Rice formula kind of says the expected number of zeros is the integral on the state space of the norm of the gradient, condition on f of x being 0, times the probability that f of x being 0. So basically, the Katz-Rice formula says the number of zeros of f on this interval from negative L to L is exactly just equal to that.
Why should I be interested in the expected number of zeros of this infinite series of Gaussian numbers?
Oh, this is just a party trick. Yeah. But on the next few slides, I'll talk about how this kind of relates to random matrices. Maybe that's more interesting. Yeah, this is just for fun. But it's a good demonstration of how to use the formula, I think. OK, so what does Katz-Rice have to do with the random matrices? Maybe this is the more relevant question. OK, so just a bit of notational setup. Let me define this to be the n-dimensional hypersphere of radius 1. Let's say x is the random matrix that we generate from our ensemble. Let me define this function. This is like a quadratic form. Let me define nabla squared to be the Riemannian gradient and Hessian on the sphere. And this pi is just the projection of some vector onto the tangent space of the hypersphere at sigma. So if this is sigma, this is the tangent plane, basically. And you don't need to know any sort of differential geometry for this. What do the gradient and Hessian look like? The spherical gradient is basically just the projection of the normal gradient onto the tangent plane. So you just think about it as the projection onto the plane of the gradient. Here, h equals sigma transpose x sigma. The gradient of that is just 2 times x times sigma. So it's just the projection of the gradient. And then basically, the Hessian is basically the projection of this matrix onto the tangent plane as well. So you have the original matrix. You shift all the eigenvalues by h of sigma. And you sort of project onto the tangent plane. Formally speaking, what you do is if ei, this is a basis for the tangent plane at sigma, then the spherical gradient is just an n-1 dimensional vector because the tangent plane has dimension n-1. And you're just sort of projecting it onto all of these basis vectors. So this is kind of yeah, you can just think about it as an n-1 dimensional vector in the basis of the tangent plane. Similarly, the Hessian is basically just an n-1 by n-1 matrix where you sort of take your basis to be the basis of the tangent plane. OK, but here's the main lemma. So the lemma is that the Riemannian gradient is 0 if and only if sigma is an eigenvector of x corresponding to the eigenvalue h of sigma. OK, so first of all, let me explain why this is true. And then I'll talk about what this has to do with Katz-Rice. So if the spherical gradient is 0, well, the spherical gradient is just the projection of the normal gradient onto the tangent plane. If the projection is 0, that means the gradient exactly needs to be parallel to sigma, right? If it's parallel, then the projection is 0. If it's if the gradient is here and the tangent plane is here, it's going to have non-zero projection. So if the spherical gradient is 0, that means the gradient is exactly parallel to sigma. And remember, the gradient is 2 times x times sigma. So that means x sigma equals some multiple of sigma. So this is an eigenvalue equation. And because these are unit vectors, just take the dot product on both sides, and you get that lambda equals this. So basically, this says that if the spherical gradient is 0, it turns out sigma is exactly an eigenvector corresponding to that eigenvalue. So this kind of relates, OK, so this exactly relates zeros of some functions with eigenvectors and eigenvalues. OK, but now you might be saying, like, OK, I thought you wanted to compute probabilities, not expected values. Like, why are you talking about expected values? The point is that, oh, yeah, OK, so I should say this. Yeah, so basically, eigenvalues of x correspond to zeros of this random function. OK, so why do you care about expected values? It turns out that these probabilities we care about decay exponentially. They're on the order of like e to the negative n times something. And it turns out that basically these expected values and those probabilities will have the same exponential order. So they're equal to leading exponential order, which is ultimately what we care about. So basically, the expected number of eigenvalues of x in that interval, by definition, is just the sum of k times the probability that there are exactly k eigenvalues there. Notice that the summation only goes to n, because n by n matrix has the most n eigenvalues. And the point is that if this expected value is of e to the negative n times some constant, like exponentially small order, that sort of means this probability also needs to be exponentially small order. Otherwise, that would just contradict the equation above. And also sort of the opposite direction. You can kind of see this intuitively. But the main point is that the quantity we care about and this expected value are of the same exponential order. And since we only want to extract this exponential order, it suffices. It's like equivalent just to compute this expected value. So that's sort of the relationship between Katz, Rice, and random matrices and the probability. We want to know the probability that you have an eigenvalue, like an irregular eigenvalue. And we have this nice tool to compute zeros of functions. And it turns out that zeros of functions of this function corresponds to eigenvalues and eigenvectors. So we can just compute that instead, because we have this like nifty formula to do that. Yeah. OK, awesome. All right. OK, so now we're going to actually compute the Katz, Rice objective. Yes, please.
Why is there no k in the if sequence?
Oh, you mean here?
Yeah, sorry. What's going on here? You're saying.
Oh, yeah. Yeah, so heuristically, you can think the probability that, so basically to leading exponential order, the probability there exists at least one eigenvalue is basically going to be the same as the probability that there exists exactly one eigenvalue. Because the probability that there exists two eigenvalues in this interval is going to be like way smaller. So the leading exponential order is like the probability that there exists one eigenvalue, basically. You can kind of think about it that way. So all of these probabilities, this probability has the same order as like the probability that there's exactly one eigenvalue. And here you're kind of just summing like polynomial number of like different terms. And those are like sub-exponential factors. So.
Up to constant factor, I can see why this could be true. But you don't have constant factor on the slides there.
Constant factor, you mean like a constant factor here?
Yeah.
Oh, yeah. So if you have a constant factor here, oh, sorry, yeah. Maybe I should have wrote it a little differently. Let's say you have a constant factor here. Basically, if you bring it into the exponent, it's going to be like one of those low-order terms. But we only care about the leading exponential rate, so we actually don't really care about that. Yeah. So I should have written like plus low-order terms or something. Yeah, that's a good point. Yeah, thanks. OK, awesome. OK, so now we're going to compute the Katz, Rice objective, recalling that the number of eigenvalues is just the number of zeros of this function times the indicator that the corresponding eigenvalue is in that interval. So this slide looks scary, but I'll try to convince you. It's not too bad, I guess. So this is the Katz, Rice objective we care about. OK, so first, I highlighted some stuff in blue. They correspond to each other to make it a little easier to follow. So instead of having h of sigma in this interval, why don't we just integrate over the possible eigenvalues in this interval and then just have the indicator that h of sigma exactly equals lambda. So you first integrate over this interval. OK, and this is kind of like the thing we saw before. Let's first apply the Katz, Rice formula to count the expected number of zeros. Well, by the Katz, Rice formula, the expected number of zeros of a function is, remember, the expected norm of its derivative. So the derivative of the gradient is just the Hessian. So you have this determinant of the Hessian. And then you condition on the event that the gradient actually is 0. And then you multiply by the density of the gradient at 0. So that's just applying the Katz, Rice formula. Oh, yeah. Now, OK, now I just want to do a quick simplification. I want to move this indicator into the conditional. Remember, to move the indicator into the conditional, then you have an extra factor of a conditional probability. It's the conditional probability that this is lambda given this equals 0. But if you take the probability of h equals lambda given this equals 0, and you multiply it by the probability that the gradient equals 0, you get like a joint density here. Yeah, you get a joint density. And that's kind of it, actually. The last line here, I just replaced the Hessian with the formula for the Hessian. I don't really know why I did that, honestly. It's not relevant in the next slide. But anyways, hopefully this is clear. But if there's any questions about this, feel free to let me know. OK. OK. OK, so if you look at this objective carefully, it only depends on the joint distribution of h, the gradient of h, and the Hessian of h, right? It's like it only depends on the distribution of this tuple. And I guess I won't go into it too carefully here. But the point is that the distribution of this tuple is actually invariant to rotations within species. Because we saw before that this quadratic form is sort of rotationally invariant to rotations is invariant to rotations within species. You can just sort of believe me that the other ones are sort of also rotationally invariant as well. So what is the point? Well, the point is that here we're integrating for sigma onto this. We're integrating our state space is sigma on this hypersphere. But as I said before, the distribution of the tuple is only going to depend on the weight profile of what these of the weight profile of the eigenvector. So the idea is that you can rotate each component of sigma so that all of its mass is on just like s coordinates, where s is the number of species. So basically, what you can do is instead of writing sigma, you can sort of just parameterize it by a very low dimensional vector. If you have like a s-dimensional vector here, you can just instead of having this really big vector sigma, you can just parameterize these last coordinates by that. So the point is, instead of integrating on the hypersphere, you now integrate over the set of x so that the unit vector is x. And here you have an extra volume term, because if this sigma 1 has norm x1, you can rotate it arbitrarily, sort of in that smaller hypersphere. So you have an extra volume term that comes out. That's where that comes from. OK, awesome. OK, now if you just sort of believe me for a second, if you believe that this objective is sort of continuous in lambda, so here lambda shows up there and there. Basically, why don't we just replace this integral over lambda with, let's say, 2 times epsilon, and you're just left with something like this. Oh, sorry, this is kind of a typo. This should be u, I guess, now that I've replaced it with u. Oh. OK. So what is the point? How do we compute this now? The point is that now we have this integral over some some state space that does not depend on n. If you can compute all of these terms, let's say they're on the order of e to the n times something. Let's say it happens to look something like this. E to the n times something, whatever, plus lower order terms. Then if you just use the Laplace method for integrals, when you take n to infinity, it's basically going to converge to e to the negative n times the infimizer of this function plus some lower order terms. Yeah, hopefully that's more or less clear. But the point here is that what is the rate function going to be? So what is the probability of an eigenvalue near u? It's exactly just going to be e to the negative n times this infimizer. And if you have an eigenvalue at u, what does the corresponding eigenvector look like? Well, it's just going to be the eigenvector whose weight profile is the optimizer of this function, basically. That's kind of what happens. So once you compute this rate function, if you want to study some sort of stuff like localization and delocalization, and you have this formula, what might happen is, for example, for certain u, for certain eigenvalues, the corresponding optimizers, have all of their weight on the first coordinate or something like that. And then if you have other u, maybe you have a more evenly distributed mass. This is how you can study eigenvalue properties and sort of these phase transitions. Maybe when u is here, u is bigger than some threshold. You have some property of the eigenvalues. When it's smaller, then you have some other properties, something like that. OK, awesome. OK, that's actually the main derivation. So let me give you a brief hint on how to, or some brief ideas on how you can even compute these terms. So first of all, these volume terms, so you can find that on Wikipedia, actually. So the volume of hyperspheres, that's on Wikipedia or ChatGPT or whatever. So that's easy to compute. Now let's look at this joint density term. I want to convince you that that's actually not too scary. So what does this joint density look like? Well, if you let EI be the basis for the tangent plane, remember that the spherical gradient is just like the projection of the gradient onto all of these basis directions. So h of sigma equals sigma transpose x sigma. That's the definition. And here you're sort of just projecting the gradient on all to these basis directions. And you can just write this as some matrix B transpose times x sigma, where B is just the matrix that consists of all of these. Oh, sorry, this should be sigma x. It consists of sigma and 2 times EI. These are all just the directions that you're sort of multiplying to. And the point is that x times sigma is just a Gaussian vector. And B here is just basically some arbitrary, it's some rotation, some change of basis. So it's actually more or less straightforward to compute the density. It requires a little bit of work, but it's like not like super difficult. You just need to like write some math or talk to ChatGPT for 2 hours, and then you're good. OK, so the last term we need to care about is this expected determinant term. OK, so what does this kind of look like? So this kind of looks scary, but if you write out the definition of this determinant, the determinant of this matrix is just basically the projection of this matrix onto the tangent plane. So it's like a n-1 by n-1 dimensional matrix. You can kind of think about this as just like taking the original matrix x minus lambda I, throwing away one row and column or something, and then just like doing some rotation. But the point is like the determinant is sort of like rotationally invariant. And you kind of imagine that if you only care about the leading exponential order, if you throw away one row and one column, it should be all good. Like you should have the same exponential order. It shouldn't like really screw anything up there. So if you just like pretend like you're not even doing this projection, then basically this determinant should approximately just be equal to this. So if you just ignore that thing, because like if you just say like, OK, you remove one row and column, you do some rotation, it shouldn't like affect things too much. To leading exponential order, you should still have the same behavior. OK, so now how do you do this? It turns out that this conditional, it is kind of annoying, but this conditional only affects like it's like a low order perturbation of this matrix. What happens is it turns out that this condition only affects like a constant number of rows and columns of this matrix. And you kind of imagine, again, if you care about the leading exponential order, and you sort of mess up like a constant number of rows and columns, you should be all good. Proving this is actually kind of difficult, but heuristically, that's kind of what happens, and you get something like this. OK, so what is this? Let me write out a couple of lines of math. So the determinant of this, by definition, is just the product of the eigenvalues. So here, lambda I are the eigenvalues, and you shift it by lambda, so you get that. OK, now let's write it in terms of exponential and log, so you get this. OK, so what is this line? Here, I'm letting mu hat be the empirical distribution of the eigenvalues. So it's like 1 over n times the sum of the delta masses. So instead of like the sum of this function, you can just integrate it with this function over like this empirical measure. And you have an extra n, because this measure is like 1 over n times the sum of the delta masses. OK, and then the whole first few minutes of my talk, I was trying to tell you that if you have a random matrix ensemble, it has a limiting spectral distribution. And the point is that this empirical distribution should converge to the limiting distribution. So basically, this object should just converge to this thing. Obviously, if you want to prove it rigorously, it's like slightly involved. But basically, heuristically, you might imagine that this is what should happen. So what does the rate function ultimately look like? The main theorem is like, suppose you have a matrix X with S species, so like S different blocks. So the weights are alpha 1, alpha 2. Recall that like alpha 1 is just a fraction of the coordinates in the first block. You have some arbitrary variance profile, this thing. And then you have like those diagonal entries, whatever, bi. Then the rate function is given like this. So let me break this down. So first of all, this thing just comes from the expected determinant term. That's kind of what we saw in the last slide. What is this thing? This thing kind of looks bad. But if you think about it, it kind of looks like X transpose covariance matrix inverse X. That's exactly the Gaussian density, right? It's basically the Gaussian density is like e to the -1/2, like X transpose covariance inverse X. So this exactly comes from that Gaussian vector that I pointed out earlier. It's just a Gaussian density. Where do these terms come from? So remember, we had those volume terms, like those volume terms that you can find on the ones you can find on Wikipedia. So basically, part of that goes to here. Those are some of the volume terms. Also, the Gaussian density has some like normalizing terms, like the 1 over square root 2 pi, whatever. That also shows up here. So while the objective looked very scary, and proving it is kind of a headache, honestly, but basically all the terms sort of naturally come out. Like it's kind of intuitive, like where at least more or less where these come from. And then if you care about the probability of an eigenvalue at u, it's just like the exponential rate. It's just going to be, so you take the log and you take -1 over n. Because, this is on the order of e to the -n times the rate function. So if you take the log, you get out -n times the rate function. You multiply by -1 over n. It's just like the infimizer here. So basically, the optimal eigenvalue configuration, eigenvector configuration, if you have an eigenvalue at u, it's just going to be the optimizers. The weight profile is just going to be the optimizers of that guy. Awesome. OK, so I'll just conclude. I'm like mostly done, so I'll just like maybe talk about a few technical details. This is not too interesting. Maybe I'll just skip that. Well, actually, OK, it's fine. Yeah. OK, so one thing I mentioned was that I kind of told you that this objective is roughly speaking continuous in lambda. So you just replace this integral with 2 epsilon. This is like slightly a simplification. It turns out that the problem is, why is this conditional thing annoying? It actually makes this thing very difficult to lower bound point-wise for each lambda. The problem is like, it's possible that x has an eigenvalue very close to lambda. And if x has an eigenvalue very close to lambda, the determinant is the product of the eigenvalues, which means that the determinant will basically be very close to 0. It would be like very small. So if you want to lower bound this, you need to kind of say like, OK, with high probability, whatever, you don't have an eigenvalue of x very close to lambda, something like that. Turns out that's kind of difficult. The solution is to use a tool from real analysis called the Hardy-Littlewood maximal inequality. What happens is we have this integral over lambda of this like expected determinant thing. The problem is it's difficult to lower bound this point-wise for each lambda. So what you can kind of do is, first of all, suppose you can replace this lambda with a u here. So you replace it with u, and u doesn't depend on lambda. If you can do that, then when you take this integral, this condition no longer depends on u, and you can move that integral over lambda into the expectation, because now the conditional doesn't depend on u. So now instead of saying like, this thing is not too small point-wise for each lambda, now you just need to show that like, OK, for a given u, for one given realization of the matrix, the eigenvalues are not too close to like all lambda in this interval, which is basically much easier. It's like an averaging thing instead of a point-wise thing. But this is the main technical detail that we got caught up on. That was kind of hard. OK, so I think I'll just conclude. So we can also do large deviations for singular values. The point is it's slightly different here. For if you have a rectangular matrix, instead of looking at sigma transpose x sigma, here you can look at sigma transpose x, and that letter is xi, I guess. The point is that the gradient here is still 0 if like sigma xi is like a left-right singular value pair or whatever. And basically all the same stuff goes through. Nothing actually really changes. This is the formula for the rectangular case. That's fine. Oh, yes. One more thing is, so we saw previously that when you have like this rank 1 perturbation, you might have an eigenvalue that jumps outside of the bulk. We can also compute the rate function for like these kind of cases, for like when you just have like a rank 1 perturbation. OK, so I guess to conclude, we present a new method for computing large deviation principles for atypical eigenvalues. OK, I do have like a few minutes. Let me just say, so there are previous methods to compute this. Maybe I can just go all the way back. There are previous methods to derive these large deviation principles. One is called the Coulomb gas method. Basically, for certain ensembles like the GOE, it turns out you can explicitly write down the joint distribution of the eigenvalues. And if you can explicitly write down the joint distribution, you can sort of compute these large deviation probabilities. But you kind of imagine that writing a joint density like isn't that easy. In most cases, you can't do that. There's also a method called spherical integrals where you consider some function like this. Long story short, the spherical integrals picks out information about the largest eigenvalue. But in our case, if you only look at the largest eigenvalue, you can't look at something like the probability of an eigenvalue, let's say, inside here, like between the bulks. And while our method can do that. So our method is like a little more general. And we do think there are some other math tools in this paper that could be useful to related problems in the field. And I think very importantly, this method can also extract information about what the eigenvectors should look like as well. And we have some follow-ups thinking about eigenvectors and also applying this to some statistical physics methods. But yeah, I think that's it. So yeah, thanks a lot, and I appreciate it. Yeah.